Computers use ones and zeros because computers are, at heart, very obedient idiots. That is the kindest way to put it. A computer is not a tiny wizard in a box, though that would explain a lot about printer behavior. A computer does not understand words, pictures, songs, games, bank accounts, cat videos, or that one spreadsheet your boss says should be simple. It understands patterns of electrical states: on, off, high voltage, low voltage, yes, no, 1, 0. That is the secret. The entire digital world, from moon missions to microwave buttons, rests on the fact that electricity can be arranged into two clear states. A computer does not want nuance. It does not want sort of. It does not want perhaps, depending on context. It wants the moral clarity of a medieval village deciding whether the bridge is up or down. 1 or 0, open or closed, signal or no signal. That sounds primitive. It is primitive. That is why it works. The reason computers use ones and zeros begins with the physical machine itself. Inside a computer are tiny electrical switches called transistors. A transistor can allow electricity to flow, or it can block it. That gives us two states. We label those states as 1 and 0 because electricity is flowing and electricity is not flowing would make computer science textbooks even more unbearable than they already are. So we use 1 and 0. A 1 means one state. A 0 means the other state. The computer does not care which one is called which. We could call them goat and turnip if we wanted. The machine would still work. But then every programming class would begin with, "Today we will learn turnip logic," and society has suffered enough. This two-state system is called binary. Bi means 2. Binary means base 2. Humans usually count in base 10, probably because most of us have 10 fingers. That is the official theory. The unofficial theory is that ancient accountants looked at their hands and said, "Good enough, send the invoice." In base 10, we have 10 digits, 0 through 9. Once we run out, we add another place. So after 9 comes 10. After 99 comes 100. Each place is worth 10 times more than the place before it. Binary works the same way, except it only has two digits, 0 and 1. Once binary runs out of digits, it adds another place. So counting in binary goes like this: 0, 1, 10, 11, 100, 101. That looks wrong at first, like a calculator got frightened by a thunderstorm. But it is the same idea as decimal counting. In decimal, the number 10 means 1 10 and 0 ones. In binary, the number 10 means 1 2 and 0 ones. Binary 10 equals decimal 2. Binary 11 means 1 2 and 1 1. That equals decimal 3. Binary 1 0 0 means 1 4, 0 2s and 0 1s. That equals decimal 4. The places in binary are powers of 2, 1s, 2s, 4s, 8s, 16s, 32s, and so on. It is like regular counting, but wearing a smaller hat. Now, why did computers settle on binary instead of decimal? After all, humans like decimal. We use it for money, measurements, taxes, and other instruments of civic gloom. Why not make computers count the way we do? Because machines need reliability more than elegance. Electricity is messy. Circuits have noise. Signals weaken. Heat interferes. Components vary. The physical world is a rude landlord. If you built a computer that had to distinguish between 10 different voltage levels, it would constantly have to decide whether a signal meant 3, 4, or 5. That is too much ambiguity. The machine would become the world's most expensive nervous clerk. Binary avoids that problem. With two states, the computer only needs to know whether the signal is low enough to count as 0 or high enough to count as 1. There is a buffer between them. Small errors do not matter as much. Think of it like a light switch. It is on or off. Easy. Now picture a light switch with 10 positions. Position 0 means darkness. Position 1 means gloomy cave. Position 2 means haunted hallway. Position 3 means sad hotel lobby. Position 4 means dentist waiting room. By position 10, The lamp has summoned an angel and melted your curtains. That system could work, but it would be annoying. Binary keeps the machine from needing to squint at the signal and ask, curious, is this a 6 or is this a 7 having a bad day? Computers prefer clean choices. This is also why binary is excellent for logic. Computers perform operations using logic gates. These are tiny circuits that take input signals and produce output signals. Since the signals are ones and zeros, the logic can be very simple. An AND gate gives a 1 only if both inputs are 1. An OR gate gives a 1 if at least one input is 1. A NOT gate flips the value. A 1 becomes 0. A 0 becomes 1. That sounds dull until you realize this is how the machine builds everything. ADAs, memory, processors, graphics, games, websites, banking systems, and your fridge's smug little touchscreen are all built from layers of tiny decisions. Yes, no, this, that, again, faster, smaller, repeat until civilization becomes dependent on password resets. Binary is simple, but simple parts can build complicated things. A single 1 or 0 is called a bit. Bit stands for binary digit. A bit is the smallest unit of digital information. It is one tiny answer to one tiny yes or no question. Is the signal on? Is this switch closed? Is this pixel bright? Is this setting enabled? One bit cannot say much. It is like a man with one word in his vocabulary. Depending on the word, he may still be elected to something, but his range is limited. Put bits together, though, and they become powerful. 8 bits make a byte. A byte can represent 256 different values, because 8 binary positions create 2 to the 8th possible combinations. That is enough to represent letters, numbers, symbols, colors, and instructions. For example, the letter A can be represented by a number. In common character encoding systems, capital A corresponds to 65. The computer stores 65 in binary. The computer does not know it is an A. It stores a pattern. The software agrees to treat that pattern as the letter A. This is how text works. Pictures work the same basic way. A digital image is made of pixels. Each pixel has color values. Those values are stored as numbers. Those numbers are stored as binary. So, when you look at a picture of a sunset, the computer is really arranging millions of little numerical instructions. The sunset is a pile of ones and zeros wearing makeup. Sound also becomes numbers. A microphone captures changes in air pressure. The computer samples those changes many times per second and records them as numerical values. Those values become binary. When you play the audio back, the speaker turns the numbers into motion, and the motion becomes sound again. So yes, your favorite song is also ones and zeros. The machine took a human voice, chopped it into numbers, stored it as binary, and then reassembled it later like a goblin with excellent filing habits. Video is the same story, with extra suffering. A video is a sequence of images, each image made of pixels, each pixel made of numbers, each number stored in binary. Add sound, timing, compression, and format rules, and now your computer can show you a raccoon stealing a donut in high definition. This is the majesty of the age. It is easy to hear ones and zeros and think computers are simple. They are not simple in the way they are arranged. They are simple in the pieces they use. A cathedral is made of stones. A novel is made of letters. A computer is made of binary states stacked into absurd towers of meaning. The greatness comes from scale. Modern chips contain billions of transistors. Each transistor is a tiny switch. They flip states at incredible speeds. When people say a computer runs at several gigahertz, they mean it performs billions of cycles per second. Billions per second. Meanwhile, I still need 3 tries to remember why I walked into the kitchen. The machine's strength is that it can do simple things very fast and very reliably. That is all computing is. Simple operations. Huge speed. Careful organization. No lunch break. Software gives those binary operations structure. A program is a list of instructions. Those instructions are represented in binary. The processor reads them and performs operations. Move this value. Add these numbers. Compare this value to that one. Jump to another instruction. Store the result. From this small grammar, we get word processors, search engines, weather models, spacecraft navigation, video games, and social media, which proves that even a miracle can be used to throw pies in the town square. Binary also allows computers to store memory. A memory cell holds a state. That state is read as 1 or 0. A hard drive, solid-state drive, or memory chip stores vast patterns of these states. When you save a file, the computer stores its binary pattern. When you open the file, the computer reads the pattern and reconstructs the thing you recognize. The file is not inside the computer the way a letter is inside an envelope. It is stored as a pattern the machine knows how to rebuild. The computer is less like a cupboard and more like a spellbook written for lightning. Binary also makes error checking possible. Since data is made of clear bits, computers can add extra bits to detect or correct mistakes. This matters when data moves across wires, through Wi-Fi, into storage, across satellites, or through the haunted swamp known as office networking. If one bit flips by accident, the system may notice. Some systems can even repair the error. This is one reason digital systems became so powerful. They can copy information with great accuracy. Analog systems often degrade with each copy. Digital systems can preserve the pattern. That is why the ones and zeros matter so much. They give us a firm foundation for representing information. Once everything can be turned into numbers and numbers can be turned into binary, the same kind of machine can handle text, sound, images, video, money, games, maps, and instructions. A computer does not need a separate soul for each kind of information. It treats everything as patterns. This is also why computers can feel strange. To us, a family photo, a tax form, and a fantasy game are completely different things. To the computer, they are all data. Different formats, different rules, different meanings for us, but still patterns of bits for the machine. The human sees a wedding photo. The computer sees a long arrangement of binary values. The human cries. The computer asks whether the file extension is supported. That is the bargain. Computers are powerful because they reduce the world to something they can handle. They do not understand meaning. They manipulate symbols. We supply the meaning. The machine supplies the speed. So why do computers use ones and zeros? Because binary matches the physical nature of electronic switches. Because 2 states are easier to detect reliably than 10. Because simple yes or no signals can be combined into logic gates. Because logic gates can be combined into processors. Because processors can manipulate numbers. Because numbers can represent letters, colors, sounds, instructions, and nearly everything else we feed into the digital furnace. The whole thing is shockingly humble at the bottom. A computer is a kingdom built from tiny gates. Each gate says yes or no. From enough yeses and nos, we get spreadsheets, movies, code, music, rockets, banking, memes, and the sacred ritual of turning something off and on again. That last one remains the highest form of technical wisdom. It is binary theology. The machine was off, then it was on, and behold, the printer remembered its purpose. Computers use ones and zeros because reality gave engineers a clean trick. Make electricity stand for 2 states, then build everything from there. It is simple enough to be reliable and powerful enough to amaze. The machine does not think like us. It counts in lightning. And somehow, from all those little flashes, we taught the glass box to sing.